This is a lesson on square roots and the Pythagorean theorem, and let's start this lesson by considering this square that is a 4-yard by 4-yard square, and let's think about what the area of that square is. And area is the number of square units on the inside of the square. So if I think most of you know that that's going to be that the area of a square is equal to side squared. And that would make sense here if you think about, I could break this into the following diagram that would really show this. Nope. So if I think of this as that's 1 yard, 2 yards, 3 yards, 4 yards, by 1, 2, 3, 4 yards, that creates these 16 square yards. So the area of this square is equal to 4 squared, which is equal to 16 square yards. So we're already kind of showing that there's indeed a relationship between actual squares and square roots, as 16 is, the square root of 16 is 4, and that's the side lengths of a square that has an area of 16 square yards. Now, just adding to our terminology, the square of a number, it just means that anytime I take a number and multiply it by itself, the result of that is the square of the number. So in the example we looked above, 16 is the square of 4. Now we need to distinguish between square roots, a primary square root of a number, and the fact that all real numbers except 0 have 2 square roots. The primary square root is the positive square root of a number. So if I'm talking about 16, 4 is the primary. So if we hear that word, all that we mean is the positive square root, because we know that 16 has 2 square roots, actually has 2 square roots, 4 and negative 4. That's because both when you square 4, I don't need those parentheses, that equals 16, and when we square negative 4, that equals 16. Okay, so next let's talk about this, the specifics of the symbolism of square roots. This part right here, most of you look at that and say, well, that means the square root of 9, but that's actually, this part's called the radical sign. And then in this instance, it actually means the, let me just write that down first. And in this case, it means it wants the primary square root of 9, which is 3. And let's make sure we understand that, because numbers, as we expressed before, have, all except 0, have more than one square root. But this symbolism confines this to the positive square root of 9. So that's called the radical sign. 9 is what we call the radicand. And we'll call 3 is the primary or positive square root of the radicand. Now, important to this discussion as we go forward is to make sure we know what rational numbers are versus irrational numbers. Since we've already discussed this, I'm going to just remind you that rational numbers can be written in A over B form, where A and b are both integers. So many numbers we work with, that can be the case. Whole numbers like 5 and 36, and negative integers, -3, -15. Those can all be written over 1, so they're rational. They can be written in A over B form. Then we have any common fractions and improper fractions, whether positive or negative. Like if I have 3/4, that's already in that form. And then it can be improper, and it can be negative, no problem there, like -10/7. So that would make all mixed numbers also rational. Terminating and repeating decimals, 2.3 and 2.3 repeating. All of those can be written in integer over integer form. Now irrational numbers, just doing a quick review of those. Those are numbers like pi and the square root of 2 and the negative square root of 11. Those are numbers that can't be written in integer over integer form. Now that is going to come into play as we, for example, define what a perfect square is. So cutting kind of straight to the essence of what a perfect square is, it's a real number that has a rational number square root. So for example, obvious ones are like 4, 25, 81, 144. So I say the primary square root of 25 is 5, which is equal to 5 over 1, right? Now you also have other perfect squares that are less obvious, like the square root of 1/4 is equal to 1/2, because 1/2 times itself, 1/2 squared equals 1/4, thus making it the square root. I could have something like, so what I'm saying there, let's add to our list there that 1/4 is a perfect square. But if you have 2.5, that's also going to be I'm sorry, not 2.5, but 2.25. 2.25 is also a perfect square because the square root of 2.5 is equal to 1.5, which is equal to 3/2, integer over integer. So let's make sure we realize that there are perfect squares other than the obvious ones that we commonly think about. Now let's actually start finding some square roots. And again, remembering this symbol means the primary square root of 49. So that's a perfect square. So we know that the primary square root of 49 is 7. Now if I put a negative out front of taking the square root, that still means the primary square root of 49, but we want the opposite of the primary square root of 49, which is equal to -7. Now, there is no number that multiplies by itself to get -49, so this is, we'll consider this to be, we could write the null set, or Yeah, that's as good as any, or I could write that for that one. Now, here's our first example of taking the square root of a non-perfect square. So 45 is not a perfect square. Now we know that we're going to use our calculators for these, but before we do that, let's think about things a little bit. The perfect squares that surround the square root of 45 are the square root of 36 and the square root of 49. So the square root of 36 is equal to 6, and the square root of 49 is equal to 7. Now the math doesn't exactly work this way. That you can't say that, okay, so there's 13 numbers between, so 49 minus 36 is 13, and 45 is 9 above 36, so 9/13, but that would get you a pretty good estimate. So we know that this is going to be more than 6.5, so I could take a quick guess here and say that this is going to be about, I'll say 6.7, that's a pure guess. But we'll use our calculator to do this. And this is the only time we're going to very quickly get away from using any estimates of square roots, but just in this section we're going to do that a little bit. So here I brought in an image of the TI-84 calculator. So if you hit second right here and then hit x squared, that's accessing this square root function right above there, and then hit 45 and enter, you'll get the square root. But before you do that, I'd like you to hit mode, and after you hit mode, you'll see that one of the choices is float, and if you move your cursor over to, we went 9 places of decimals there just so we get practice with rounding. So before you take that square root, go to mode, and then the second choice down I think will be float, and scroll your cursor over to 9 places and hit enter, and then that'll put your square root to 9 places when we do that. So when I do the square root of 25 on my TI-84 calculator, I got that is, it shows me that is, I'm going to write approximately, because when you are taking the square root of a non-perfect square, you're getting a decimal that doesn't terminate or repeat. So this is, but it shows me 9 decimal places. And I don't know if that 9th digit is a 2 rounded up to a 2 or it's a 1, but we don't need to know that. We're going to round to 3 decimal places, so we're looking right here, and since this 2 is 4 or below, we're going to leave that approximation at 6.708. So next I'm looking at taking the square root of this fraction 16/81. So one tip-off that this is actually a perfect square is that both 16 and 81 are perfect squares. And so the square root of 16 is 4, the square root of 81 is 9, so that is just going to be equal to 4/9. So that means 16/81 was a perfect square. In this next one, I have a negative sign in front of this. Well, this just means the opposite of the square root of this fraction. Well, 1's a perfect square, 144. So once again, this is a rational square root. So that means 1/44 is a perfect square. So we're going to say negative 1/12. Now that's not saying that negative 1/12 is a square root of 1/144th. It just means it's the opposite of the primary square root of that, which is 1/12. It's the opposite of the primary square root of this, which is 1/12. If I have 2 and 1/4, now at first glance that appears not to be a perfect square, but if you play around with it for a little bit and realize that that's actually the square root of 9/4, and 9's a perfect square, 4 is a perfect square, so that equals 3/2. On the other hand, you might think 1/2 is a perfect square, but it's actually not, because 1 is a perfect square, however 2 is not. So if we want to approximate this square root, we'd have to take the square root of 0.5 on our calculator. So when I do that, I get that this is equal to, having my float to 9 places, it says, and I'll put the negative out front, 0.707161, I'm sorry, 106,781. We know a decimal pattern that doesn't repeat or terminate goes from there, but if we want to round to the third decimal place, we're looking at that 1 right there, and since that's a 1, it's not 5 or greater, we'll leave that at the approximate square root of 1/2 is 0.0707. Now looking down below, I have the square root of 7.374. Well, before I go on my calculator and see what that is, it's possible it's a perfect square, but not likely. I think I made that number up when I was making up this lesson, so unless I stumbled on one. But we know that the nearest square roots, the square root of 4 is 2, and the square root of 9 is 3, so a rough approximation would be, I don't know, let's say 2.8, I'll say, but let's actually do it. So the seconds on my calculator, the second square root of 7.342, so it actually is equal to 2.7096125518, and if I look here, this time the 6 is 5 or bigger, so I'll have to take that up, and so that's going to mean 2.710, because the 9 will get bumped up to a 10, and that'll bump the 0 up to a 1. Now let's do a refresher on the Pythagorean theorem. We did this in 7th grade math, but this, remember, only applies to right triangles. Remember, we call the two side lengths that make up the right angle of a right triangle the legs, and the side opposite the right angle is called the hypotenuse. And that this theorem that's been proved many times says that if I square the length of the two legs and sum those, that'll equal the square of the hypotenuse. So let's look at some examples here. Here's a pretty simple one. We have two legs are 5 and 12, so we're going to say here that it doesn't matter which is A and which is B, so we'll say 5 squared plus 12 squared, and we'll call that part C right there, equals C squared. And so that gets us that 25 plus 144 equals C squared. So that's 169 equals C squared. And even though C could be 13 or negative 13, we're talking about geometry here. So C equals the primary square root of 169, which is 13 inches. Now, I'm looking over here at this example right here. So I'm looking at this right triangle here, so we call an isosceles right triangle. But once again, the two legs are given. And this one, I have, again, looking for C. So I'll say 8 squared plus 8 squared equals C squared. And I have 64 plus 64 equals 128. or I can say, before I do that, I can say equals c squared. So c squared equals 128. Now this time 128 is not a perfect square, but I can get an approximation of that side length. So c equals the square root of 128. I know that's somewhere between 120, the square root of 121, which is 11, and the square root of 12, which is 140, square root of 144, which is 12. So I know it's going to be, let's see, 121. That's pretty much halfway in between. I mean, it's pretty close to halfway in between, so it's pretty close. It's going to be pretty close to 11.5. But let's see. Let's take the square root of 128, and that is equal to, it says 11.3. So yeah, that's right. It's a little closer to 121 than it is. Well, it's a lot closer to 121. So I'm going to say that is, if I look at my decimal here, it's approximately equal to 11.3137. We're going to round right here. I'm not going to put all the decimal places this time. You get the idea. That bumps the 3 up to a 4. So C is approximately equal to 11.313, and that units on that one were feet. Now let's focus on this example right over here. So let's next look at this triangle right here, where I have a leg of 12 meters. I don't know this leg right there, so we're going to call that, I call it A or B. I'm just going to call it B. And so I'm going to say 12 is my leg that I'm calling A, so 12 squared plus B squared equals 37 squared. 37 here's the hypotenuse, because it's opposite the, you can see, whoops, that it's opposite the right angle right there. So continuing on with my calculations, I've got 144 plus B squared equals 37 squared, which is 1369. When I subtract 144 from each side, I get B squared equals 1225. I know that that's somewhere between 30 and 40. Since it's got a 5 at the end, I can be pretty suspicious that it's going to be 35 squared, which it is if you check it on your calculator. So that would equal to 35 meters. And then finishing up on this page with this example below, I have, once again, where I'm given a leg, missing another leg, and have the hypotenuse. It's opposite the right angle. So I'm going to call this, just so I can show you that there's no difference in A and B, I'll call that A this time. So A squared plus 14 squared equals 31 squared. And A squared plus 196 equals 961. Subtract 196, and that's 5, and 15 minus 9 is 6, so that's 765 is A squared. So again, on this one, I know it's between, if I squared, I have 25 squared, that's 625. And 30 squared is 900, so it's a little bit closer to 25. So I have A equals the square root of 765, and square root of 765 is equal to approximately 27.6586. 27.6586. If I round to the thousands place, I'll have that means it'll bounce up to 27.659 kilometers. And so this final problem, let's find the distance from home plate to second base, and realizing that a baseball diamond is actually a square. This is a right angle right here. So you can think of home to first and first to second as the legs of a right triangle. And what we're looking for is this distance from home to second base. That's what a catcher has to throw out a runner trying to steal second base. And so that's just a good old-fashioned right triangle. So you have the two legs are the distance from home to first, and then the other leg is the distance from first to second, and then C is the distance from home to second base. And what we have here is 8,100 plus 8,100 equals C squared. So that's 16,200 equals C squared. We know that 162 is not a perfect square, so we're going to C is equal to the square root of that. We'll have to use our calculators for that. And when I do that, I get that C is approximately equal to 127.2792. So that 2 right there, whoops, that 2 right there does not round that 9 up, so we'll just stick with that 127.279 feet. And that is the end of the lesson.